In this video we discuss the representation theorem for polyhedral sets, and the polyhedral set that we are going to consider is given by X, which is the set of all x's in Rn satisfying the constraints given by Ax is less than or equal to b and non-negativity of all the variables. This is a typical feasible set for a linear program, so we have non-negativity constraints here, and we assume that this polyhedral set is non-empty. Alright, then we have the following statements. X has a non-empty finite set of extreme points given by x1 through xk. So why is it true? First of all, the set is non-empty, right? And then we also have the non-negativity constraints, which imply that this polyhedral set does not contain a line. And we know from a previously established theorem that a polyhedral set has an extreme point if and only if it does not contain a line. And clearly, because of the non-negativity constraints, we don't have a line in this set, therefore there must be at least one extreme point. So this shows that we have a non-empty set of extreme points. Now, why is this set finite? Because we have a finite number of defining hyperplanes, and let's say if we assume that the matrix A has m rows and n columns, then the total number of defining hyperplanes is given by m plus n, and then we know that for a point within the polyhedral set to be an extreme point, it must be on the intersection of n linearly independent defining hyperplanes. So we need to choose n linearly independent defining hyperplanes from the set of n plus m total defining hyperplanes. Therefore, n plus m choose n will give us an upper bound on the number of extreme points that we have. So this shows that you have a non-empty and finite set of extreme points. The next statement we have here is that the set of extreme directions is empty if and only if x is bounded. Alright, so first, if we assume that x is bounded, then clearly there are no recession directions. And when there are no recession directions, there cannot be any extreme directions. Now, if x is unbounded, then there are recession directions, and the recession cone is given by d of x, which is the set of d's such that AD is less than or equal to 0, and then D is greater than or equal to 0. Alright, so this is D of x, and then we can define the set D of normalized recession directions by introducing a constraint. So first let me copy this AD is less than or equal to 0, D greater than or equal to 0, and then we can normalize vector D by enforcing the condition that E transposed times D is equal to 1. This is done in order to avoid the ambiguity with the recession directions, so we just require that the sum of the entries of vector D is equal to 1. Then this polyhedron D is bounded, and we can show that the extreme directions of the set X are in fact extreme points of this polyhedral set D. In fact, if we remove the 0 vector from here, and in fact this is what we usually do for the recession cone doesn't include the 0 vector, then all the remaining extreme points of this set, they will involve this hyperplane here given by the summation of all di's equal to 1, and all these extreme points will be corresponding to extreme directions of the set X. Okay, So now once you have the unbounded set X, every extreme point of this polyhedral set, and there will be extreme points because, look, this is a bounded set, right? So we are guaranteed to have some extreme points, and each extreme point is going to correspond to an extreme direction of X. Therefore, this statement here is established. Then the next statement we have here is that if X is not bounded, it will have a finite number of extreme directions d1 through dl for some L. So why is it the case? Again, looking at this polyhedral set D here, we know that all the extreme points of this polyhedral set correspond to the extreme directions of the set X. And this correspondence is 1 to 1. Therefore, because we have a finite number of extreme points for this set, we will have a finite number of extreme directions for X. Alright, so this establishes the third statement. Finally, the main statement of this theorem is that a point X bar belongs to our polyhedral set X capital if and only if it can be written as the following sum. So X bar is given by the summation of lambda i's xi's for I between 1 and k. So this is the convex combination of the extreme points of our set X. Alright, it is a convex combination because, as we can see here, the summation of lambda i's is equal to 1 and lambda i's are all non-negative, and then plus the summation for j between 1 and L of mu j's dj's. So here dj's are the extreme directions for our set X, and mu j's are some non-negative multipliers. Okay, so essentially our X bar is represented as a convex combination of extreme points plus some non-negative combination of extreme directions. And this is if and only if statement, meaning that if X bar is in this polyhedral set, then there is this representation in terms of extreme points and directions. And on the other hand, if X bar can be represented as this combination here, then X bar must belong to X. And in fact, this latter part is trivial to establish. So if X bar can be represented like this here, then the convex combination of the extreme point clearly belongs to the set X, because the set X is convex, right? And then once you have the convex combination of these extreme points, if you move along the extreme directions, then by the definition of extreme directions, you will still remain in the set X. Okay, so the part where X is represented like this, then it belongs to the set X capital, is easy. And to establish the other directions, we need to show that if X bar is in the set X capital, then it can be written as this combination here. Alright, so for this we will just sketch the proof and we'll skip the details, but I'm going to give the idea of how the proof proceeds. First, let's consider a situation when our set X capital is bounded. So we have something like this here. So let's say this is our polyhedral set. Alright, so this is X capital. Then this is a two-dimensional example, of course, and our n is equal to 2 in this case, right? So let's consider an arbitrary point X bar in our set X capital. So what we're gonna do with this point X bar, we will look at the maximum number of linearly independent defining hyperplanes intersecting at that point. Say if that number is 2, so let's say if your X bar is like this, it's on the intersection of two defining hyperplanes, then obviously it is an extreme point, and there is nothing to prove, right? You have x bar is just equal to lambda 1 x1, let's say, if this is your extreme point x1, and this lambda 1 is equal to 1, and the rest of lambdas are zeros, and we are done, right? Now, if the maximum number of linearly independent defining hyperplanes is less than n, then this means that our x bar is not an extreme point, and let's say if that number is 1, then x bar belongs to one of the defining hyperplanes here, right? So let's say it is here. Now, since x bar is not an extreme point, it can be represented as a convex combination of 2 points from the set x capital, right? So let's say we have these 2 points right here, and x bar is the convex combination of these 2 points. Now, if we try to look at the corresponding directions from x bar to one of these 2 points and to the other one, then we will obtain some rays, right? So let's say if I'm moving in this direction, then my ray will point this way. And because we assume that this polyhedral set is bounded, if I move along this ray, eventually I'm going to hit some constraint, and I will obtain a point on the intersection of 2 linearly independent defining hyperplanes. And this will give me one extreme point. And then if I move in the opposite direction, so what is going to happen? It's the same thing. So this ray also cannot be completely within the feasible region, because we assume that this polyhedral set is bounded, and then we are going to hit some other constraint if we move in this direction. So, and this will give us the other extreme point, and then x bar can be represented as a convex combination of these 2 extreme points. Now we can apply a similar logic to the case when our x bar is inside the region here, so meaning that the number of defining hyperplanes passing through this point x bar is 0, which is 2 less than the dimension of the space we are working with, right? So in this case, again, we take 2 points such that x bar is a convex combination of these 2 points, and let's say we take one of them and shoot a ray from x bar to that point, and we keep going until we hit the boundary, and this will give us this point right here. And now for this point there is one defining hyperplane that passes through it, and we apply the same logic as before for this x bar right here to obtain an extreme point of our feasible region. Okay, so now that we obtained this extreme point, let's call it y, let's say, we can move in the direction x bar minus y, and we can shoot a ray from y towards x bar, and again we are going to hit the boundary of our feasible region. Alright, so say this is some other point that we'll call it y prime. So then x bar is a convex combination of y and y prime. And then for point y prime, now it belongs to one of the defining hyperplanes, and we can apply the same logic as we used for this x bar here to obtain 2 extreme points, this one and this one, for which y prime will be a convex combination of these 2 extreme points. Alright, so combining these 2 facts, that x bar is a convex combination of y and y prime, and then replacing y prime with the convex combination of these 2 points, we will obtain the proof that x bar is in fact a convex combination of these 3 points. Alright, so it will be a convex combination of 3 extreme points of our feasible region, and the statement is established for this case, and so on. So we can apply this logic to any point x bar within the feasible region, and we can obtain its representation as a convex combination of extreme points of our polyhedral set. And again, in this case, we assumed that our polyhedral set was bounded, so there are no extreme directions here, so this part would disappear, right? So we wouldn't have mu j's dj's, there wouldn't be mu j's at all here, and x bar would be represented as a convex combination of extreme points of our polyhedral set. Now, if we have some recession directions, the situation gets a little more complicated, so let's consider an example here where we do have the directions of unboundedness. So, say we have a set like this, so this will be our feasible region x capital, okay? Now, in this case, there are a couple of extreme points, and then we have a couple of extreme directions. Okay? So what do we do in this case? So we apply a simple trick similar to what we had here when we were normalizing the recession directions. What we are going to do, we will introduce a hyperplane here, which will be E transposed times x is less than or equal to some big M. Alright? So we introduce this hyperplane after we select the point x bar. So let's say if your point x bar is somewhere here, then the way we are going to select this big M here is in a way that E transposed x bar is less than M. Not only that, E transpose times xi is less than M for every extreme point. So essentially we want to build this hyperplane in a way that if I add the constraint, then all the extreme points of the feasible region that we had before will still be within our feasible region. Alright, so all of the extreme points of the original set X satisfy this constraint, and now we have this modified set X bar. So this will be this polyhedral set right here. Alright, so it adds a couple of new extreme points, as you see, and these extreme points will actually correspond to extreme directions of our original set X. And now we essentially reduce this case to the previous one where we had the bounded polyhedron. So now x bar can be represented as a convex combination of the extreme points of our bounded polyhedron x bar here, x bar capital. And then we'll need to replace the extreme points that correspond to this new hyperplane that we added with the sum of extreme point of the original set and the extreme direction of the original set. So for example, this extreme point right here can be represented as a sum of this extreme point and the extreme direction that takes us to this point from this extreme point, right? So after we do this replacement, we will obtain exactly what we need here. Alright, so for multipliers for the extreme points of the original set, we will still have their convex combination, and then for the multipliers that we have here for the extreme directions, there will be just some non-negative mu j's, and as a result, we will obtain this representation that we were looking for. Alright, so this is just the idea of the proof, and we are going to skip the details.